Welcome, guys. In this video, we are going to start on the next big chapter on hypothesis testing. In chapter number 6 on estimation, we were mainly concerned with finding numerical estimates of parameters in the form of either single points or confidence intervals. But that's not always the case. In many experimental situations, the conclusion to be drawn is not numerical and is more phrased as a choice between two conflicting theories or hypotheses. A court psychiatrist, for example, might be called upon to pronounce an accused murderer either sane or insane. The Food Drug Administration, for instance, must decide whether a new flu vaccine is effective or ineffective. So, for instance, if someone asks you a question whether new treatment for, let's say, melanoma is effective or not, giving your answer in the form of confidence interval, for instance, if you say that confidence interval, 95% confidence interval for recovery rate is in range of from, let's say, 29.3 to 32.1%, then it doesn't specifically answer the question whether the new drug is effective or not. So in these cases, we use the following statistical tool known as hypothesis testing. In general, hypothesis testing concerns trying to decide whether a parameter or vector of parameters theta lies in one subset of the parameter space or in its complement. In this chapter 6, specifically in this course, we'll only have one parameter of interest. So we'll be mainly interested in deciding whether a parameter theta lies in one interval or in its complement, or in other interval. Okay, so in chapter 6 on estimation, we were building confidence intervals for parameters. So we found an interval of plausible values for our parameter. And you can already see a connection between these two. And in fact, there is a duality between hypothesis testing and confidence intervals. And later in this chapter, we'll see that we can answer hypothesis tests questions by looking at confidence intervals. So for instance, if we come back to our previous example on deciding whether a new treatment for melanoma is effective or not, if we'll build confidence interval, then we can answer our hypothesis test based on that confidence interval too. We'll see that later in the chapter. The general idea of hypothesis test is following. Consider a statistical problem involving a parameter theta whose value is unknown but must lie in a certain parameter space omega. So in the rest of this course, we'll be working with hypothesis testing for parameter theta, which is going to be only either population mean or population variance or standard deviation. And parameter space omega is a fancy name for all possible values of our parameter. Suppose now that omega can be partitioned into two disjoint subsets, omega 0 and omega 1. So let's assume that our parameter space is test results, and let's assume that test results can be from 0 to 100. Then we can partition our parameter space into two subsets, two disjoint subsets, let's say test scores from 0 to 50 and from 50 to 100. And the statistician is interested in whether theta lies in omega 0 or omega 1. So we are interested in whether our parameter omega, let's say, mean of scores of students in some school or class lies in range from 0 to 50 or from 50 to 100. We shall let H naught denote the hypothesis that theta lies in first omega 0 subset of our parameter space, and let H1 denote the hypothesis. We'll also call this as alternative hypothesis that theta lies in omega 1. Since subsets omega 0 and omega 1 are disjoint and their union is equal to the whole parameter space, exactly one of these two hypotheses must be true. And the statistician must decide which of the hypotheses H0 or H1 appears to be true. So problem of this type in which there are only two possible decisions is called a problem of hypothesis testing. So again, H0 is null hypothesis and H1 is alternative hypothesis. If we, up to this point, we can treat H0 and H1 in the same way. However, they treat it quite differently. So again, null and alternative hypothesis. Null hypothesis denoted by H0 is a hypothesis that is to be tested. The alternative hypothesis denoted by H1 or in some cases HA or H2, H3. So you can have different subscripts for this letter, but H0 is always H0. Null hypothesis is always denoted by H0. So alternative hypothesis denoted by H1 is a hypothesis that in some sense contradicts to the null hypothesis. And null hypothesis is assumed to be true and statistical evidence is required to reject it in favor of a research or alternative hypothesis. So our null hypothesis is some preconceived conservative idea about the values of our parameters. So let's assume that you want to test whether biology students, for instance, in Nazarbayev University have a higher IQ than some other major students. In this case, your null hypothesis is going to be a conservative idea that biology students majoring in biology have the same IQ as the rest of the university. And your alternative hypothesis is then either can be to decide whether biology students have greater IQ scores or lower IQ scores. So null hypothesis is conservative idea. Or for instance, let's say you are testing whether healing crystals, for instance, can help treating COVID, then your conservative idea, null hypothesis, is that healing crystals are ineffective in treating COVID. You can also consider hypothesis testing as being in a courtroom, and the decision must be made whether the defendant is guilty or not guilty. And null hypothesis is an assumption as in a courtroom that defendant is not guilty until proven otherwise. So null hypothesis is that our defendant is not guilty. And the decision of our hypothesis testing is then going to be either rejecting H0, rejecting null hypothesis in favor of alternative hypothesis, or failing to reject H0. We usually don't say accept H0 or accept H1, since if we reject H0 or fail to reject H0, for instance, if we fail to reject H0, it doesn't mean that we have proven H0. So for instance, if you, let's assume that average IQ scores of university students is 110. And then if you fail to reject that biology students have IQ scores greater than 110, it doesn't mean that you have gathered evidence to prove that biology students have IQ scores averaging 110. Okay, so now about this, let's talk about decision rule, or basically what evidence and how much of it is required to prove that our defendant is guilty or not guilty. Imagine an automobile company looking for additives that might increase gas mileage. So company is looking for, let's say, some chemicals to add to their fuels that will probably increase gas mileage. As a pilot study, they sent 30 cars fueled with a new additive on a road trip from Boston to Los Angeles. Without the additive, those same cars are known to average 25 miles per gallon. So this is that. We also can see that this is going to be our conservative idea, is that new fuel additive is ineffective, and mean of gas mileage is 25 miles per gallon. Let Y1 to Y30 denote the mileages recorded by each of the cars during the cross-country test run. So this is our sample of size 30. We assume that yi's are normally distributed with an unknown mean mu. Furthermore, suppose that prior experience with road tests of this type suggests that sigma standard deviation will be equal to 2.4. Suppose it turns out that the 30 cars average y bar is equal to 26.3 miles per gallon with the additive. So we can see that this value y bar is greater than average mileage, which might suggest us that new fuel additive might be effective. So what should the company conclude? So our question is whether this here is enough evidence to show that new fuel additive is effective or not. Okay. So basically what's happening here is that we have, let's say, some population of, let's assume that this is whole population of cars with new fuel additive. And we don't know new average mileage of these cars. So we are drawing a sample of 30 cars. Those are yi's. N is equal to 30. Our sample mean was equal to 26.3. And our question here is that enough evidence to show that gas mileage of cars with fuel additive is greater than 25 miles per gallon? Then our null hypothesis is that our defendant is not guilty, or the new fuel additive isn't effective, and gas mileage of cars that use the new fuel additive is the same as all the other normal cars. And our alternative hypothesis is that our fuel additive is effective, and in fact, gas mileage of cars using a new fuel additive is greater than 25 miles per gallon. Then our logical guess for deciding whether the new fuel additive is effective or not should be based on following. So we have our sample of yi's coming from normal distribution with under assumption of null hypothesis that they come from population with mu that is equal to 25 miles per gallon. And then our logical guess is that if y bar is too much greater than 25, let's say if y bar is equal to 100, this might strongly suggest us that new fuel additive is effective. Or if we got the value of y bar that is too close to 25, let's say 25.01, then it might suggest us that new fuel additive isn't effective, and the cars using that are the same as all the other cars. Okay, now our question is, after which values of y bar such that y bar is greater than some value, we should reject our null hypothesis. So what should be the value? Should it be the value of 30 or maybe 26, maybe 27? So we have to decide after which value, which is denoted here as y bar star, or some critical value or some threshold value, after which we are going to reject our null hypothesis, and we'll decide that the new field additive might be effective. Here, after some value of y bar star critical, we'll reject our null hypothesis, and up to this point, if our values are too close to 25, we're assuming that our null hypothesis is true and the new field additive is not effective. Okay. Now let's try to pick some values, and let's see how do they perform. Let's pick this threshold value as 25.25. Is that good enough? Then let's calculate probability that we'll reject H naught under assumption that our null hypothesis is true, or mu is equal to 25 miles per gallon. So population mean is equal to 25 miles per gallon. And we reject H naught then when y bar is greater than this threshold value of 25.25. Then if we assume that this y bar comes from normal distribution with mean of 25, this distribution is also known as null distribution. So null distribution is the distribution of our population under assumption that null hypothesis is true. So here is our null distribution. This is normal distribution with mean at 25. Then we'll reject H naught when y bar is greater than 25.25, normalizing minus mu divided by standard deviation over root of n. Then we find this probability as probability of standard normal being greater than 0.57 and is equal to 0.28. So 28%. So it looks like critical value of 25.25 isn't good enough, since 28%. So basically what is represented by this probability is the probability that we decide that our defendant is not guilty, is guilty when in fact he's not guilty. So it means that we'll send an innocent person to a prison. So 28% is an inappropriately large probability for making this kind of incorrect inference. No jury, for example, would convict a defendant knowing that it had 28% chance of sending an innocent person to jail. So here our null distributions and probability that if our sample comes from this null distribution, if those y bars come from this yi's come from normal distributions, then what is the probability to get value of y bars that is greater than 25.25? So it seems like this y bar critical is too close. So we'll get too large area of 28%. So probability of 28% of making incorrect decision, of incorrectly rejecting our null hypothesis. Let's try to pick different value for y bar star critical. Let's try 26.5. Is that good enough? So let's look at probability of rejecting H naught under assumption that H naught is true. So probability is that y bar, our sample mean, is going to be greater than 26.5 under assumption that our sample comes from normal with mean of 25. Then standardizing, we find that probability is that standard normal greater than 3.42 is equal to this small value of 0.03%. So it seems that this probability is too small. And in fact, when we'll get to the chapter on power of a test, we'll see that this probability is related to the following probability: probability of failing to reject H naught under an assumption that H1 is true. So this probability that we reject H naught when H naught is true. So here, this is probability of incorrect decision. Probability of incorrect decision, and having this value to be small is good. So when this value is low, it's good. This probability here, probability of failing to reject H naught when in fact alternative hypothesis is true. This probability is also, this event is also defines an incorrect decision. And this probability being low is also good. However, when we increase this probability of rejecting H naught when H naught is true, we are going to increase the value of that probability of failing to reject H naught when alternative hypothesis is true. So we'll see when we'll get to the section on power of a test that there is always a trade-off. We cannot pick very small value for that, since it will drastically increase this probability of this incorrect decision. So answer is no. Requiring that much evidence before rejecting H naught would be analogous to a jury not returning a guilty verdict unless the prosecutor could produce a room full of eyewitnesses, an obvious motive, a signed confession, and a dead body in the trunk of a defendant's car. Okay, so here is our null distribution under assumptions that mu is equal to 25. And the probability that y bar under this assumption that y bar critical is going to be, that y bar is going to be greater than y bar critical of 26.5 is very small. So very small area in the right tail here. Okay, now then the question is, which value should we pick for this y bar critical, after which we are going to reject our null hypothesis. And in many experiments, this probability is set to be to 0.05 to 5%. So this is the standard golden rule. So then if this probability is equal to 0.05, probability that y bar is greater than our critical value under assumption that null hypothesis is true is given as 0.05. Then if we standardize, we'll find that this probability is equal to probability of standard normal being greater than this value here. And we know that if we look at standard normal, if we want 5% lying in the right tail here, then this point corresponds to 1.64. So this score is equal to 1.64. Now, if we substitute 1.64, if we equate this to 1.64, we find that this critical value corresponds to y bar star of 20.718. Okay, so now, which means that our company's rule for deciding whether a fuel additive is effective or not is completely set. So if y bar, the mean gas mileage of sample of the cars that we are testing, is greater than 25.718, then we need to reject H naught. Then we reject that fuel additive isn't effective, which might suggest us that fuel additive maybe it is effective. Okay, and then if y bar is less than this value, critical values, then we fail to reject our null hypothesis. Okay, so let's go over a couple of the definitions provided here. any function of the observed data whose numerical value dictates whether H naught is accepted or rejected is called a test statistic. The set of values for the test statistic that results in the null hypothesis being rejected is called the critical region and is denoted by C. The particular point in C that separates the rejection region from the acceptance region is called the critical value. So in our problems that we considered previously, both y bar, our sample mean, and this z-score that we calculated using normalizing y bar qualify as test statistics. So if sample mean is used, the associated critical region would be written as the following set of values for y bar such that y bar is greater than 25.72. So our critical value that we calculated before. If the decision rule is framed in terms of z values, then C is a region, is a set of values of z such that this normalized quantity of y bar is greater than 1.64, 95th quantile of normal distribution. Okay, so usually when we'll proceed in this course and in the literature that you will see, we usually just calculate this z-score, and we use z-scores or t-scores, as we'll see later, as our main test statistic. We rarely calculate our critical values and critical region in terms of our sample means, because it's easier and quicker. Okay, so in our previous examples, then let's calculate our test statistic. So our test statistic is normalized value of y bar. So then if we substitute 26.2 for y bar, then our test statistics is 2.74, and which is greater than 1.64, meaning that we reject H naught. So basically, it means that if we look at our null distribution, and if we look at its 95th quantile, then y bar of 26.2 corresponds to this value that is far to the left, to the right of 1.64, which is equal to 2.74, meaning that under an assumption of your null hypothesis, it's unlikely that you get a sample mean of 26.2. If your points in your sample are sampled from normal distribution with mean of mu is equal to 25. Meaning that we are going to reject H naught at a level of significance of 0.05. Okay, let's go over the following two definitions now. If null hypothesis of mu is equal to mu naught is rejected using 5% decision rule, the difference between y bar and mu naught, so y bar 26.2 in our example, and mu naught was 25, is said to be statistically significant. So the difference between the following two values is statistically significant. And the probability that the test statistic lies in the critical region when H naught is true is called the level of significance and denoted by alpha. So in our case, level of significance was 5%. So basically it means that under our null hypothesis, we have a 5% probability of drawing samples that will result in y bar that is far to the right of our mean here. Okay. So also, if we define this in terms of rejection and as acceptance regions, then this region to the left of 1.64 is acceptance region. And this region to the right of 1.64 is rejection region. Okay, and 1.64 is our critical value. And 2.74 that we calculated using Y bar is our test statistic. One-sided versus two-sided alternative. If there is reason to believe before any data are collected that the parameter being tested is necessarily restricted to one particular side of H naught, then H1 is defined to reflect that limitation, and we say that the alternative hypothesis is one-sided. However, we'll discuss this a bit more. This is rarely the case. Two variations are possible. H alternative can be one-sided to the left. In this case, alternative hypothesis is as mean is less than mu naught, or it can be one-sided to the right. Mean is greater than mu naught. If no such a priori information is available, the alternative hypothesis needs to accommodate the possibility that the true parameter value might lie on either side of mu naught. Any such alternative is said to be two-sided. So, for instance, if you are conducting a hypothesis test on test whether a new treatment is effective or not, then the results might be following. Either the new treatment is effective and maybe it increases recovery rate, or it's not effective and maybe even it's going to worsen the situation and reduce the recovery rate. In these cases, you should use two tests with two-sided alternatives. So by the way, this one-sided test where we were testing alternative hypothesis that mean is greater mu naught, we're considering only the case that gas mileage of cars is going to be increased only. So that was one-sided or one-tailed test. Okay, so tests for H naught, mean is equal to mu naught versus mean is less than mu naught. Alternative hypothesis that mean is greater than mu naught. So these two are one-sided or one-tailed tests. And in case when we are unsure and mean can be greater or less than mu naught, then we test that test for alternative hypothesis that mean is not equal to mu naught. So this test is two-tailed test. So in one-tailed test, for instance, in this one that we have seen in gas mileage example, we were assuming that our null distribution is given with mean of mu naught that was 25. And then if we are drawing, if we draw Y bars that lie far to the right from our mean in this region that was corresponding to 5%, then we would reject our null hypothesis that our sample of Y ice comes from this population here. In the case of two-tailed test, let's assume if we were unsure whether our gas mileage would be increased or decreased, then we would conduct the following hypothesis test. So on level of significance of alpha is equal to 5% or 0.05, then we would split this area in the right tail in the two tails. And our rejection region that was previously only focused in right tail here would be split in the following left and right tails with 2.5% lying in each tail. So if we get values of Y bar that are far to the left, that are far smaller than our null hypothesis mean, or far to the right, or much greater than our null hypothesis mean, then we would reject our null hypothesis. And these two tails would correspond to rejection region in case if we would conduct the following hypothesis test of with null hypothesis mu being equal to 25 and alternative hypothesis being mu being not equal to 25. So we would consider both cases that mean could be less or could be greater. Okay. So again, in the gas line example, it was tacitly assumed that the additive either would have no effect, in which case mu would be equal to 25 and H naught would be true, or would increase gas mileage, implying that the true mean would lie somewhere to the right of H naught. Accordingly, we wrote alternative hypothesis as mu is greater than 25. If we had reason to suspect, though, that the additive might interfere with the gas line's combustibility and possibly decrease mileage, it would have been necessary to use two-sided alternatives tests. So guys, you might be already guessing and thinking, when should we know? You might smell something fishy here. When should we know prior to collecting data whether our mean is going to be greater or smaller than some value? And your notion is correct. And in fact, there is a big debate whether to use tests with one-sided alternatives or not. One main reasoning is that researchers should separate their beliefs from scientific method. And here are some good literature giving valid reasons why tests with one-sided alternatives should not be used. And here's this one phrase from it. So now almost all authorities now agree that one-tailed tests are rarely, if ever, appropriate. And most journals, especially journals, clinical journals, they would require that you use two-tailed tests. Okay, now also another good reason is that, for instance, if we consider, let's say, one-tailed test, let's say again, consider our case with gas mileage, one-tailed test, our critical value was equal to 1.67, if I'm not wrong. And in case if we would conduct two-tailed tests, so this value of 1.67 would correspond to, or was it 1.64? So this area would correspond to a 5% level of significance. Now, if we conduct two-tailed test, then we would have this 5% area split in both two tails, meaning that our critical value, after which we should reject our null hypothesis, would be further to the right of these critical values. And on 5% significance level, if we would conduct Z test, the critical value would be 1.64 or minus 1.64. So to get a positive result on the same level of significance, by positive result, we mean that we reject H naught, our null hypothesis. It's easier to reject null hypothesis when you conduct one-tailed test on the same level of significance rather than two-tailed test. As you can see, this value is greater than 1.67. So, which means that you need more evidence to reject H naught when you use a two-tailed test was on the same levels of significance if you compare it to one-sided test. Okay, and also it's going to make our course a bit easier as we proceed. So we are going to be only working with tests with two-sided alternatives. All problems on midterms and exams will be two-tailed tests. Okay. All right. So the test that we conducted in gas mileage example is known as one sample Z test. So as you recall, let's come back to our example on gas mileage here. So first thing to note is that population standard deviation was known. It was equal to 2.4. And then another thing to note is that our yi's were normally distributed. So yi's are normally distributed. So if these two assumptions are about population are valid, then we use one sample Z test in case when sigma is known, and our test statistic are given as Z scores. Okay, so let yi be random sample of size n from normal distribution where the population standard deviation is known. Then let your test statistic be y bar minus mu naught over sigma, or so over standard error. To test h naught, null hypothesis mu is equal to mu naught versus alternative hypothesis mu is greater mu naught. So this is one-sided test at the alpha level of significance. Then we should reject h naught if our test statistic is greater than this critical value, which corresponds to normal quantile 1 minus alpha. And to test null hypothesis mu is equal to mu naught versus alternative hypothesis mu is less than mu naught at the alpha level of significance, reject h naught if your test statistic is less than minus this critical value. And this corresponds to 1 minus alpha's quantile of normal distribution, of standard normal distribution. Okay, and so out of this, you can remember only this line here, since, as we said before, all our tests will be two-sided tests. To test h naught, mu is equal to mu naught versus h alternative mu is not equal to mu naught at the alpha level of significance, reject h naught if your test statistic is either less than minus this critical value. So we want 5% of area lying in both tails. Then we would have alpha over 2 area lying in this tail and alpha over 2 area lying in this tail over here. So our critical points then would be z 1 minus alpha over 2 or minus z 1 minus alpha over 2, which is also equal to z alpha over 2, but I would recommend just always using the same quantile. Okay, so now up to this point, we've almost covered the backbone for hypothesis testing. And what's going to happen next in the following two chapters, chapter 7 and chapter 8, the things that are going to change is that we said that this is one sample test. We had a single sample that is going to change to two samples. So we'll consider cases when we'll have two samples coming from different populations, and they would have some unknown parameters, let's say mu1 and mu2, and we'll do hypothesis testing comparing the means of the following two populations. The next thing that is going to change is that we are going to vary z-test to t-test. So we should use z-test only in the case when sigma is known. And most commonly, sigma is not going to be known, and we are going to use t-test. Even if your sample is large, as we said for confidence interval, we should always use a t-test rather than z-test, even if your sample is large. If your sample will be large, then your t quantiles and z quantiles will be the same, so you are safe if you use t-test. So we'll mainly be working with t-tests. Also, so this is one sample z-test for population mean. Since our now, so we were testing hypothesis about mean, and this parameter might change to variance, and we'll consider hypothesis tests for variance of population.